All right, so let's finish up this lecture, and then I'll demonstrate the first couple projects. You can get started on that. So, instructions. Let's talk about a few kinds of instructions out there. So move source to destination. That's the most common instruction. Moves data from one location to another. This Windows developers use the Intel format with the destination first. So you move this thing to that thing. This is the Intel. The other format is AT&T, which is the other way. So here you'd move 48 to ESP, and here you would subtract 48 from ESP, and here you would subtract 48 from ESP. And you can see they put these $0x in front of something to indicate it's hexadecimal here, and they put the source here and the destination there. So it's pretty annoying. All right, anyway, that's the thing to know about. Windows developers typically use Intel, and Linux developers typically use AT&T. So you'll see them both, and you sort of get used to it. But at first I found it quite confusing. Yeah?
AT&T format probably the barrel laboratory format.
What's that?
The AT&T format, the barrel laboratory format.
Yeah, AT&T, yeah, it came from Bell Labs, yeah. All right, so remember indirect addressing. Putting brackets around something means to interpret it as an address, and it refers to that memory location. All right, so here's some examples. Move EAX, EBX. That'll copy EBX into EAX. The contents of EBX will go into EAX. This one will put 42 in EAX, the immediate value 42. This one will put that memory address with that long address, 4037C4, whatever is at that location in memory, which will be moved into EAX. It'll copy 4 bytes from there, 32 bits. All these are 32-bit instructions because we have 32-bit processor. And this one will take EBX, interpret that as an address, find the contents of that address, and put it in EAX. And this one is one you see a lot for moving large amounts of data, EBX plus ESI times 4. Another thing that's annoying is that addresses address bytes, but instructions move words. And the words for a 32-bit processor are 32 bits, so they're 4 bytes long. So if you wanted to move a whole range of data, starting at EBX, you would set ESI equal to 0 and execute this command, and then set ESI equal 1, 2, 3, and 4 and execute this command, and you move forward by 4 bytes every time. So you'd have the EBX is the start of the memory location you're moving, and ESI is the counter that counts through the words, and you move forward 4 bytes at a time. So that's a thing to know, and all of it is because of history. In the early days, you had 8-bit processors, and you referred to bytes, and that was all there was. But when your processors got bigger, they didn't change the convention of how to address memory. So memory continued to be addressed by the byte, not by the word. So, like that little Indian thing, it's one of those details that can get you confused. And so here's a crazy instruction: load effective address. You want the value EBX plus 8, and for some reason you can't just move the value EBX plus 8. What you have to do is load the effective address of EBX plus 8. This will calculate the EBX plus 8, and that's the answer. It does not look it up in memory. It calculates the address of this indirect thing. So it's a screwy one. Anyway, if you did a move, you would move the contents of that address into here. If you load effective address, you load the address of that into here. So that's a subtle one. All right. And so here's another example. So you're going to do move EAX bracket EBX plus 8. So EBX is B3140. EBX plus 8 is down here. So that's the word, this word that contains 20. That's what would be moved by this command, move EX bracket EBX plus 8. If you did load effective address, it would put the value, this value plus 8, B30048. So that's an example showing you the difference between them. All right, and we're not going to be using that command, I think, in any of our exploits here, so I wouldn't worry about it too much, but this shows you the kind of careful thinking you have to go into to really understand exactly what these machine language instructions do. So you have all the things you might want: subtract, add, increment to add one, decrement to subtract one, multiply and divide. There's even floating point instructions, although I've never used any of them. Those are for like games with 3D rotation or something. NOP you use all the time. NOP does nothing. It's an instruction, no operation. You might think there's no reason to even have this instruction, but the main reason it exists is because some instructions have to be on a 4-byte word. You can't just put them at any address. So you have to put the next instruction at 4 bytes, but the instruction before it might have a different length, like the one we did before, move EBX42 was 5 bytes long. So if you had that instruction, and the next instruction has to be on a 4-byte word, you'd need 3 bytes of padding, and that's what NOP is for. You'd put NOP, 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 just to pad it to hit the boundary of the next 4-byte word. That's the sort of thing. However, that's the original intention of it, but attackers use it all the time because when you are making an exploit, you inject some code, then you try to run your code, and you have to figure out where your code is in memory. And the problem is you usually don't know exactly where your code is on your target machine because you have a practice machine you develop your exploit on, but the target you're attacking might not really be the same. It might not have exactly the same version of Windows or other things, so you might be wrong in the address. So what you do is instead of just injecting your code, you inject a NOP sled before your code, like 1,000 NOPs before your code. Then you jump into that. Now if you're wrong by even 100 bytes or 200 bytes, it'll still work. As long as you hit any of the NOPs, it'll do NOP, 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 and then your egg, which is the attack you want. So you'll see NOP sleds all the time in attacks. A NOP sled makes your attack more reliable. It will work on more of the target machines, even if some of your assumptions about the target machine are wrong. All right, so the stack is where we're going to do most of our attacks. It's this last in, first out system. So every time you're in a routine running, the ESP is the top of the current stack frame and the EBP is the bottom of the current stack frame. And that's the temporary memory used for temporary storage of data while you're in that routine. You can put data on the stack with push and you can remove it with pop. Push will put something on top of the stack and pop will take the data off the top of the stack. You can now calls a subroutine. And that involves creating a new stack frame. Leave comes back from a subroutine, which is like a pop command. It takes data off the stack, enters a command, return, returns. These are things to enter and return from functions, and both of them involve changing the stack. And function calls. So you have a small program that does something like printf. All right, at the beginning of every function, there is a prologue, and this is what prepares the stack frame. It allocates new memory on the stack to store the local variables. And the epilogue is what restores the stack and then returns back to what you left off in the program that called it. And we're going to see these in detail. So here's what you will have as your program runs. You'll start with, say, Windows. Then you launch something like Microsoft Word. It has a stack frame. And then Microsoft Word, you click like open some subroutine of some kind, like open a menu, and then in the menu you say print something. So now you're in print, you're in the menu, you're in Microsoft Word, and you're in Windows all at once in different frames. And when you're done printing, it will return from print back to here and free this memory. So it's available for reuse, but the stack is what keeps track of all those breadcrumbs to find your way back home. All right, let's see. What's the difference between byte addressable and word addressable memory? I'm not aware of any word addressable memory. Everything I know continues to address memory by bytes, even 64-bit, 32, and 16-bit machines. So you just get used to the fact that the addresses are, you skip over several bytes at a time when you're counting through a memory region. Let's see, is it based on processor? Yeah, as far as, I'm not aware of any processors that address memory by word. In principle, they could, but they don't, as far as I can tell. Is garbage collection and epilogue a garbage collection? The only garbage collection I know about is on SSDs, and that's run by the SSD firmware in the background while you're not using it. I think there is something in Java called garbage collection, and I don't quite know how it works. But nothing like that is done by these functions. These functions are too simple for that. That would be a higher level operating system command. So inside a stack frame, you will have the ESP is here, so that's and then you'll have variables stored here, things that are used inside there, and then you'll have the old EBP and the return address at the end of it. This is the extended base pointer, which is the bottom of the calling function's stack frame, and this is the return address to go to. So that's the point. And here's arguments that were brought in from the function above. So the point here is this return address controls where it's going to go when it's done with this routine, and it tries to return to the one above it. So if we can overwrite one of these variables and go out the end and change this return address, we gain control of the box. And that's what buffer overflow exploits do. All right, there's a conditional called test that doesn't alter them. Test EAX. EAX just has a result of 0 if EAX is 0. You can also compare two things to set the 0 flag if the arguments are equal. These are just ways to create an if statement where it will decide whether some condition is true or not. And then you can do a jump 0 or a jump not 0. So you can test something and then do a jump 0, and that adds up to an if statement. If it's 0, it will go somewhere. This will jump to that location if the last command created a result of 0, and this will jump if the last command created a non-zero result. All right, so in C, we'll do a little bit of C programming because C is very close to assembly language. It's the highest level language that's closest to assembly language. So if you want to understand assembly language, you write a little bit in C and compile it, and then you can see how it works. So in C, everything starts with the main, argc and char ** argv. These are the parameters that are fed into the function. All right. And so if you copy foo to bar, then this is the copy command, and the argument count is 3. The name of the command itself counts, and both of the arguments. This is the Linux command, which are all written in C, by the way. So Linux command cp will copy the file foo to the file bar. And that is a C program with 3 arguments. The first one is cp, the next one is foo, and the next one is bar. That's how arguments enter a C function. All right, and now you can recognize C code in assembly. So here, for example, you define an integer that's a number, and then you increment it, C plus number plus plus. So in assembler, you would define a word starting at 0, named number, and then here you'd move number into EAX, increment EAX, and move EAX into number. Now this is something you often have to do. You might wish that there was a command that would increment something in memory, but you only have the instructions that were built into the hardware of the microprocessor. And the Intel processor does not have increment memory location. So you have to do it in 3 steps. You have to take the memory location, put it in an address, increment it, and then put it back out there. This, by the way, you have to do this much more in ARM. ARM won't let you do hardly anything except on registers. So every time you do anything, you have to put it in a register, do it, and then put it back out in memory. Intel has a bunch of things that do refer to memory, but not the one here. So this is what you see, several assembly language instructions to do one line of C. That's why programmers prefer to write in high-level languages like C. It's easier, but this is what the compiler will turn it into. And so here, you define a number, and if number is less than 0, then do something. So you define the number, now you move the number into EAX, then you do an OR of EAX to EAX. That's like a compare. It will have the result of 0 if EAX was 0. And then you jump, if it's greater than or equal to, down here, because the ... stuff will happen if it is less than 0. So if I'm not quite sure how this OR turns into greater than or equal, and have to pay a little more careful attention. But anyway, the combination of doing the OR and then jumping if it's greater than or equal is how they do that. And
The OR is just 0, I think.
OR is what?
0.
Yeah, OR will, I know, OR, A or B, no, XOR would be 0. And OR will preserve the ones. Yeah. And so if any part of this was 1, then it will be greater than 0, and therefore it'll jump here. But if it was 0, this would not be true. Yeah. All right. And here's an array of 4, and now you set the array number 2 to 9. I see some questions here. You mentioned heap earlier, an individual stack for each of the routines. There's only one heap. Actually, in Linux, there's only one heap, and all parts of your program store it. In Windows, there's a bunch of heaps. You can define as many as you want, and they're all separate. They're much more complicated, and we'll talk about that when we get there. It's a good question. All right, so here's how you define 4 items in a row, all set to 0, called array. That's 4 items, and each one of them is a word, a 32-bit word. And here you move 2 into EBX, and then you take array and offset it by 2 values and put 9 in there. So this is how you would refer to something by what you could call word indexing. the second element of the array is moving forward 32 bits at a time. So it's 64 bits in from the start of it. Anyway, that's, again, how these commands add up to look like that C command, to do what the C command does. And here's the last one to do a little bit of math. So you want to do a triangle between width and height. So you're going to, they define an array here, and then you calculate area equals width times height. So the only part here I thought was interesting was just to see the multiplication. There is an imul command to do integer multiplication in here. And as you see, it takes more assembly language commands to do it, but that's all I thought was interesting about this one, to see the multiplication. There is hardware multiplication and hardware division. In fact, modern processors even have hardware AES encryption. There's a bunch of fancy commands to do fancy things, but we don't need any of them. All we need is the simple stuff for the exploits we're going to do. So let's do one more Kahoot, which will be this one here. All right. There you go. That looks like one of yours with all the faces. I think we've got everybody. All right, so the instructions at the start of a function, what are they? That's the prologue that create the stack frame by adjusting ESP and EBP. What mnemonic enters a function? All right, that's call. Okay, what mnemonic will multiply two numbers? That's imul is integer multiplication. There's also floating point multiplication, but that's integer multiplication. All right, which one compares two numbers? All right, test compares two numbers. All right, which one's is special for buffer overflows? you make a NOP sled with hundreds of NOPs in a row, which is not something a compiler would ever do or a normal programmer would ever do. All right, what mnemonic shrinks the stack? That's pop, takes the top value off the stack, making the stack smaller. All right, that's SID. Root. All right. And you have it, okay? All right, good. All right, so let me stop this recording, because that's it for the lecture. And